Okay, so first reminder, if you have recitation tomorrow, you're going to print out this file that I emailed you about and I posted here. Right here in this post in Readings and Homework, it says recitation, Friday the 23rd. You're going to print out that right there and bring it to recitation tomorrow. Okay? You don't have to work on it before. You don't have to work on it before. Okay? I will post Tuesday's homework today sometime, just like normal in the normal place. What else we got? Remember that I'm videoing every class. The YouTube links are here in the class videos area. And then also remember that you've got 6 people with office hours spread out throughout the week that you are welcome to just show up during those hours and get help. They're waiting for you. All of us are waiting for you. And we're all equally nice and welcoming, okay? So don't be afraid. Some of you have just aced math classes all your life. It's been no problem. You didn't need to get much extra help. For some of you, those days may be over. This is a hard class. It's going to get hard. In a couple weeks here, it's going to get really hard, okay? And so this is why we're offering so much support. You have a huge network of support here. So please take advantage of that. Don't think you can breeze through. Get help. It's there, okay? What else? Oh, so with recitation, remember, so recitation is mandatory. We're taking attendance, and basically, so there's not like a recitation part of your grade, but if you don't show up, then over time, your overall grade in the course starts accelerating downward by percent, 2%, 4%, okay? So you have to go. But it's not just about just showing up and being there. We're really trying to have the very best activities and time for you to get help in the class. So there'll be time for question and answer on homework and problems that we're doing that we don't have time for in lecture. And then also other activities and group work that we're working hard to pick those activities that are going to be the most beneficial for you to succeed. Okay? So please, of course, you have to come, but be engaged, and it should help you improve in the course, not just be something you have to go to. Okay? Any questions about just stuff in general like this? Announcements. Okay, so if you want to get out graphing calculator, open up your laptops. Oh, okay, yeah, you can get it out, but there actually is one thing I want to do before that. So we're not quite using it yet. I want to just give you an overview of calculus. So we're doing all this we're laying this groundwork with quantitative analysis, understanding multiplication and division, and how quantities change together, how we represent that with graphs, how we use functions and function notation to model that. And all this stuff is crucial for when we get to the calculus and it gets hard. So don't have a mindset of getting through these assignments or problems and I got the right answer and I'm going to move on. Okay, you have to have a mindset of all this stuff that we're doing. I'm picking the material that we're covering right now, which may feel a little bit like review, but I'm picking it very specifically because it's the most important things that you have to have down cold. Okay? You can't be fumbling with this stuff when we get to the calculus, the hard stuff. You have to have this down cold. So we're not just filling up time here at the beginning of the course with something fun to do. This is all very, very, very important for the harder stuff later. It's the environment and functions, graphs, function notation is the environment that we're going to live in calculus. And so when the ideas and the concepts are hard and intertwined, that stuff needs to be in place. You can't struggle with that, or you'll really struggle. And this is the experience we have with lots of students. We get into the middle of the course, and they don't know function notation, okay? Or they don't know how to read a graph, okay? So that's why we're spending so much time on this, so we don't get tripped up by these basic foundations when we get to the calculus. So what is calculus about? Okay, it's 2 fundamental problems that calculus addresses. And the first is, you know how much of something there is, so you have some amount of something, and you want to know how fast that amount is changing. This is 1/2 of calculus. You know how much of it you have, and you want to know how fast it's changing. Second half is, you know how fast it's changing, and you want to know how much you have. Okay? So it's reverse. So you know how fast the quantity is changing. You want to know how much of that quantity that you have. Okay? So the first one is what we call differential calculus. You know the amount, and you want to know how fast it's changing. The second one is integral calculus. All right, you know what the rate is, you know how fast it's changing, and you want to be able to calculate the amount of that quantity. Okay? All of calculus can be summed up in a nutshell with kind of these two processes. Okay? So differential calculus is about how fast it's changing. That's what we focus on, how fast it's changing. But when something's changing, those changes accumulate into an amount. And so then that is pointing at integral calculus, which is about amount. You have the amount. Well, any amount of something builds up in bits at a certain rate. And that points us back at differential calculus. So they're really, two sides of one idea, or two sides of the same coin, and that one big idea is rate of change. Okay? So that's what this course is about, rate of change. How fast it's changing, and how much has accumulated. Okay? So we'll go back to this. We'll go back to this and talk about this as we're working through. These are the two main ideas. You know how much of something there is. You want to know how fast it's changing. You know how fast something is changing. You want to know how much of it there is. So we'll be in the middle of the course, and I'll say, okay, what are we working on right now? So you got to know that before doing any of the details. What is our goal at the moment? What are we working on? Which of these two are we working on? Not everyone will get it right. Okay? Okay? So, any questions on just this overview of calculus? So we always keep in mind the big picture of what we're doing. Okay? Always keep in mind the big picture. So I want to focus in on this problem about you had the sunflower problem that you turned in today. I want to do a little bit of what you did, but then build on that and do a whole bunch of other things. And so today's work is going to be bringing together graphs, understanding graphs, function notation, how it plays into graphs, and using graphing calculator to do all that, because that's what you're going to be doing all semester. Okay? The great thing about graphing calculator is it's based on a system. These command lines are exactly the mathematics that we're doing. They're exactly the mathematics that we're doing. It uses function and function notation to produce the graphs very consistently with what we're learning on paper. Okay? So it's a great tool, not only to display and see it visually, but then as a learning tool, building. So actually building graphing calculator files requires that you understand the mathematics. So it's really an excellent tool. So here's that problem. The height of a sunflower is modeled by this function. H of t equals that expression, the rule. H of t, the height of the centimeter, t days after the seed germinates. The function is only valid the first 10 days after germination, 0 to 10. Okay, so before we get to the graphing calculator, let's just ask a few questions here. So first of all, can you articulate very clearly and precisely what does h of 6.4 represent, and what does h of q equals 6.14 represent? Talk to the person next to you just for 30 seconds. What do those things represent? Go. Oops. Okay, so when you see this expression, h of 6.14, h of 6.14, what does that represent? Right here in the gray sweatshirt. Yeah.
So h of 6.14 is the input. So our 6.14 is the input.
Okay.
So it's saying that days. How tall is sunflower?
Okay, so it's how tall the sunflower is, the height of the sunflower in centimeters, which height? Specifically at 6.14 days, right? It's the output when the input is 6.14. So it's the height in centimeters at 6.14 days. What about h of q equals 6.14? Right here, in front.
Well, this time 6.14 is the output.
Okay.
So we're trying to find out after how many days is the sunflower 6.14 centimeters tall.
And what represents how many days in this statement?
Q.
Q, right. So Q would represent how many days it would take to reach a height of 6.14 centimeters. Does it make sense? So that's review. Well, a lot of this is review, but we got to keep practicing it. Because in the future, we get in this big complicated problem and you see an expression like h of 6.14, and so it just, boom, it's just be, oh, that's the output quantity when that input's 6.14. Just like that. You should know it just as well as that. Okay? All right, so let's show that. So here I've defined the function. Okay, so I use D for days. I could have used anything. It just, when you're defining the function in Graphing Calculator, so go ahead and do this now. So go ahead. You can use anything. Try to stay away from the ones that are they're built-in, that have built-in functions in Graphing Calculator. But you could use x. You could do h of x equals, and then have all x's here. In that case, x doesn't mean the x-axis. It's in a function definition, so it's just this placeholder for the input. Okay, but then in other command lines, x will mean the x-axis or graphing. Okay, but so now if you enter now in the next command line, if you put h of 6.0, and remember when you're defining functions and using functions, you got this is really important. Control 9. Not Shift 9. Shift 9 is normal parentheses for grouping and multiplication. Control 9 is function notation. So that's going to be something you watch out for. And you'll see, if I were to do Shift 9, so here's to say, you see how it's farther, see how those parentheses are a little bit farther away from the F. You see that? With the H, those parentheses are right up against the H. And I just did F Shift 9. What it's going to do here is going to multiply the value of F times whatever's in the parentheses. It's not seeing that as a function. Okay? So make sure you use Control 9. And you'll know when it's a little bit closer, those parentheses are hugging right up against your function name. Wow. Okay. So, in the homework, it said, without using any graphs or solving algebraically for t, determine as closely as you can how long it takes for the sunflower to reach a height of 40 centimeters. Show function notation or solution wherever possible. And I tried to put some comments in and sent you an email and said, you can use the function as much as you want. Just don't solve for the time, and don't use the graph to do this. So how can we do this? How can we figure out when it reaches 40 centimeters? Any ideas?
Can you just set the output to 40 and solve for...
Well, that's what you're not allowed to do, right? You're not allowed to solve for the input.
You can just estimate. Like,
Okay, so yeah, exactly.
Kept on putting in different amount of days, so the output's getting closer and closer.
Yeah, so here we are. So let's try something, okay? We're trying to get 40 centimeters. Here I put in 3 days. I got 10.8. What's happening over these 10 days? Is the sunflower going up and down? It's going up. So what am I going to do? So I'm at 10.8 centimeters. How am I going to change the number of days to get closer to 40? As time goes by, we're expecting the height of the sunflower to go up. So I'll change it to 5. There's 27. Change it to 7. 44. So now I'm too high. So now I'll try 6. See how convenient Graphing Calculator is? I define the function. All I have to do is just keep changing the input, and it gives me the new values. So now I'm at 36. So we're between 6 and 7. So try 6.5. A little bit less than 6.5. Try 6.4. Now we're between 6.4 and 6.5. So try 6.45. Getting really close. A little bit less. 6.44. A little bit more. It's pretty dang close. Okay? Questions on part B? This was the intent of that problem, that you just try different numbers of days, calculate those outputs until you can hone in on 40 centimeters tall. Practice using the function, practice using function notation. Okay, now we want to represent, so you had part C, was to represent the change in the sunflower's height between 7 and 9 days. Okay, before I do that, is there a question? Before I do that, I want to talk about, is there a question? Okay. Before we talk about representing the change in the sunflower's height, let's just talk about a change in the number of days. So here we're starting at 7, so down here, without graphing yet. So we're not graphing yet. We're just still talking about using the function and quantities. So down here, maybe, yep. So here's 7, and here's 9. And so we're talking about a change, first of all, a change in the number of days from day 7 to day 9. What's the amount of change in time there? What's the amount of change in time?
2 days.
2 days. Okay, we represent that by using delta. So delta t represents, so t is the variable of number of days since germination. Delta t is a change in the number of days since germination. So in this case, we're focusing on starting 7 days from germination to 9 days from germination. And so the amount of change in time is 2. And if this was, say, 9.86 and this was 7.92, how would you get that number? So 2 is very easy, but where did it really come from? Final value of the quantity minus initial value of the quantity. Okay? Final value minus initial value. So this is a new quantity now, a new quantity based on the quantity t, the variable t, which represents a change in that value. Okay, so what if I started here at 1 and went to 3? Is that the same change in t or a different change in t? Is that the same or different?
Same.
Is it the same or different? I think it's different. It's different. Is it the same or different? Yes! It's the same and it's different. How is it the same?
It's the same that there's only 2 days.
The amount of change is the same. The amount of change is a 2-day change. Okay? How is it different? Obviously.
The height is different.
Okay, the height, but how is just looking at time, how is that change of 2 days different? It's a different time period, starting at 1 day, ending at 3 days, versus starting at 7 days, ending at 9 days. Okay? So the change in a value is kind of a different animal, right? So with t, there's only one t equals 4, and there's only one t equals 8, right? 8 days after germination. There's no ambiguity. But if you say delta t, the change in time, well, that could be applied anywhere at any starting time. So a change of time of 2 could start at t equals 1, could start at t equals 6, could start at t equals 10.1. It's the same amount of change, but it's a different change because it's, in this case, a different time period. Does it make sense? Okay, so that's delta t. So we want the change in height. So the change in height of the sunflower starting at day 7, ending at day 9. Well, if delta t is 2, if the change in t is 2, then what about h of, I'm just going to take this delta t of 2 and do h of 2, and that'll give me the change in height.
No.
Yes or no?
No.
That should feel very uncomfortable. What does h of 2 represent? What is h of 2? It is a specific height at 2 days after germination. This is not a change in height. This is not a change in height. So this has been tried by calculus students throughout the ages, okay? you've got a change in height of 2, or change in time of 2, you want a change in height, so you do h of 2. But remember, if we really know our function notation, that is the height at 2 days. So, no. So how are we going to get the change in height? Well, it's the same idea as this. Final value minus initial value gives you the amount of change. Final value, so we need the final value of height, which is h of 9 minus h of 7. Okay, that's going to give us the change in height of the sunflower as we go from day 7 to day 9. Notice this is final value of input, initial value of input. Because you need the final value of output minus the initial value of output to get the change in output that you want. Okay, and that would be we don't want to say delta h. H is not a variable. H is the whole relationship. So if we had some other variable for the height, say, I don't know, little h. So maybe little h is a variable that represents the height. Then we could say this is delta little h. But it wouldn't be delta big H, because big H is just the name of the function, represents the whole relationship. It doesn't represent the output. Okay? Just capital H by itself does not represent the output. You need H of, parentheses, input. That represents output. Okay? So, here, the beauty of graphing calculator. I can just now put in h9 minus h of 7. It knows what the h function is and just applies it to both and gives me a difference. Is that equal to h of 3 minus h of 1, since they're both a change of 2? No, not even close. Look, the change in height from 1 to 3 days is 9.8 centimeters. The change in height from 7 to 9 days, 14.6 centimeters. Just to prove the point, is either of those equal to h of 2? H of 2 is something totally different. That's the height after 2 days. That's 4.8 centimeters. Okay, so now when we start dealing with changes in the function, we have to be really precise, okay, about what we mean. So we have to get it right, because it changes the value if you change which time period you're looking at, or which interval of input you're looking at. It's going to change what the change in output is. And this does not calculate a change in output. This is a particular output. Okay, cool. So let's do some graphing. So now I want to graph this. I've got h of d equals this. I've defined my function according to the rule. And so what about this? Is this going to graph? So y equals h of d. So I got the right idea here. Y equals, that's going to tell graphing calculator graph. Remember, x and y tells graphing calculator, I want you to graph whatever this is. So y equals the output h of d. Is that going to graph it?
It is, but it's not going to graph.
All right, so what will it graph? I'm going to turn this on. What is it going to graph? Okay, I got a line. I got a horizontal line, okay? For any given time, I got the same height. What's going on here? Talk to the person next to you. What is going on here? I'll just zoom. Yeah. Zooming, right? So that's these buttons down here, zoom. By using Option and Command, you can zoom in on one axis or the other. You see the little arrows that pop up? Okay, what's going on here? I got a line. Yes, sir.
So we haven't defined d as anything, so it's just 1.
Okay.
That's why y equals 1.
Okay, so we haven't defined d as anything, so it's just going to default d equals 1, and so that's why I graphed y equals 1. Half right. Half right. Yeah. Okay. Okay, but we're explaining this. So yes, you're right. You're right. But we want to explain this, and he got a lot of it right, but not quite. Yes, sir.
D is a constant.
Okay.
Instance, so when you plug the 1 in, it just comes out with a number. So all of the x, all of y values.
Okay, so it's not graphing y equals d. So d, yes, d is 1, but it's not graphing 1 because d is 1. Why is it graphing 1? Well, what's it graphing? It's scratching h of d. What is h of d?
Oh,
What is h of d?
The output.
The output of the function h when the input is d. And what is d? 1. So it's not graphing d equals 1. It's graphing the output of the function when the input is 1. And what is that? Well, that happens to be 1 also. So it's 1 not because d is 1. It's because h of d is 1. H of 1 is also 1. If you plug 1 into that, you get negative 0.1 plus 1.7 minus 0.6, which is also 1, coincidentally. Okay? All right, so this is just graphing a constant. The output of h when the input is d, in this case, the default is 1. So in these two lines, you have to see that in these two lines, the letter d is being used very differently. Graphing calculator is using d very differently. In defining the function, it's just using d as a placeholder for input. It doesn't care what that symbol is. You could use a, you could use b. Okay? So you could use x, you could use y, you could use z, you could use anything. And in that function definition, it's just a placeholder holding the place of input. Telling graphing calculator, okay, whatever goes in the parentheses, I'm going to put that in the rule wherever you see that same symbol. But now in the next line, we're using it. Now d is a parameter. It's like a variable. And if we haven't defined it, it's going to, by default, it's going to set it equal to 1, as you see right there. So now this is a number, right? This is a number. It's the output of h when the input is 1. Okay? So if I put in 2 here, what will I get?
That y value and output is h.
Right. I'm going to get a constant y value, whatever the height of that plant is, when the input is 2. And it's just going to graph it as a constant, because h of 2 is a constant. H of 2 is a number. Doesn't make sense. So we want to graph it. Someone over here was telling me how to graph it. How do I really want to graph it then? You said it before. Go ahead.
Y equals
Okay, h of x. X stands for every value on the x-axis. So it's going to take all the values on the x-axis, throw them into the function all together, and give us all the outputs. That will graph the function. So we want to do y equals h of x. Okay, so I want you to this is the view we're going to look at. So I want you to recreate this view of the graph. Okay, so we're graphing the height of the sunflower from 0 to 10. I want you to recreate this exact view. So practice using your zooming. Okay, that's practice using the zooming. And so if you're Mac, it's Option and Command to either change just the x-axis or just the y-axis. And if you're on PC, is it what? Shift and Control? Is that right? Shift and Control. One of those gives you just zooming on the x, and then the other one just zooming on the y. Okay. So we want to define the function. You should have done that already. Now we want to actually graph it from 0 to 10. And this is time to practice using the zoom to get it to look just like mine. Questions? Okay, so less than or equal to. Are you Mac or PC? PC? What is it? Control Shift minus and plus. So Control Shift and then less than will give you less than or equal to. And Control Shift. Got it? Other questions? Mac is just option less than, option greater than. Other questions? So this is the view we want. This is the view we want.
Is there a way to just...
Yeah.
When you do the shift and control view, left, up, down, left, to right, is there a way you can actually control how much it zooms in? Because in order for me to get that, I can't do it.
So just get the same scales, right? So you should be able to get this scale should come up. The 2, 4, 6, 8, and then the 10, 20, 30, 40. It should do that.
Okay, it's different.
It just may be different, like because the way your screen is.
Actually, no, it's not right. So, yeah, do this. It goes just a little too far out.
No, but see, you're at 1, 2, 3, 4, so you want to zoom out on x-axis to get 2, 4, 6, 8. Change the numbers. There you go. And now on this one, you want that 20, 40, 60, 80, so you want to zoom in or Y. I think it's okay. So let's talk about, so we had this change from 7 to 9. And so let's just represent that real fast on the graph. So h of, so here's 7, and here's 9. Oh, so, okay, before that. So when you see this graph, what do you think? What is your image of what this graph is showing? Tell the person next to you. Tell the person next to you. When you look at a graph, what is your image of what it's displaying? What is it showing? Did you say this? This is what you should have said. You think of time and height changing together. So you think of starting at day 0, and we're going to let the time start, and time is going to go by, and this coordination of time and height is going to emerge, point by point, point by point. So when you see a graph, this should be your image of it. That point by point, these associated values of time and height emerge as time increases. So it's not just a wire sitting on a white paper, right? It's about how the quantities change together. It's mapping out point by point how the quantities are changing together. Every time and associated height. Every time and associated height. Every time and associated height. Okay? So we'll keep revisiting that. This is the way you want to imagine graphs. Okay. All right. So where are we at here? So at 7, how do we represent what's happening at 7 days? Here's 7 days. How does the graph represent what's going on at 7 days? With what? A point, right? A point. This one. And how does it represent what's going on at 9 days? Another point. I'm going to show you how to actually graph points in a second here, but I have a different. So how can we, here we are at 7 days, and what's the y-coordinate? What's the exact y-coordinate of that point? So they're saying it down here. How about back there? What's the exact coordinate of this point at 7 days? H of 7. So this ordered pair is? 7 comma H of 7 gives us the exact height at 7 days. And where do we find, so we had trouble on the top hat, Where do we find h of 7 in this picture? Y-axis. Here's where we find h of 7, whatever that height is. The values themselves are not, the point is not the values themselves. It's a representation of the two values taken together. The values are displayed on the axes. So here's our 7, our x coordinate. Here's our h of 7 over here. All right, and so similarly, this is 9 and h of 9. Now I want to represent this change in time from 7 to 9. So starting from here, I can represent that change in time from 7 to 9 as a segment. Should I go up, down, left, or right? I want the change in time from 7 to 9.
Right.
Right. So that line right there represents our delta t of 2, specifically starting at 7, ending at 9 days after germination. And then, when that happens, so what happened to the height when those 2 days went by? It went from what to what? H of 7 to h of 9. And so we can show that like this. We're at h of 7. And so I called the quantity little h, so that's delta h. And so this would be that number we calculated before. The length of that segment is h of 9 minus h of 7, or the change in height.
Not h of 2.
Exactly. H of 2 is what? This down here. Here's h of 2. Totally different than the change in height as time went from 7 to 9. We're going to do lots of this. So representing changes on the graph. Representing changes on the graph. Crucially important. Okay. So points. So to get a point, you're going to hit Control 2. So start a new line. Hold down Control and hit 2, and you get a vertical vector thingy like this, brackets. So you're just going to plug in the x and y coordinates. So I'll just plug in 6 and 30. You can choose the color. I got red. So it just plotted the point 6, 30. So Control 2 plots a point. Should have done this before we did that last thing and actually plotted the nice, but we're not there yet. So now, another thing you can do for points is you can click on the curve and crosshairs come up, and you can drag those crosshairs. And when you do that, if you look up in the corner, you get the current corresponding values of x and y for your crosshairs, or for where you're at. So you can move it up here. I'm at 7.6875 and 40.4222. So just put the arrow on the graph and click, and those should pop up, and then you can drag it. And then wherever you're at any given moment, it'll tell you the coordinates of where you're zoomed in on. If the crosshairs are open and you just hit the zoom button, it will not zoom in the center of the graph anymore. It'll zoom at the center of the crosshairs. Okay, so if I'm way up here and I hit zoom in, it'll zoom in there instead of the center of your graph. Okay? As a hint, as a tip. Okay, so put the crosshairs on t equals 4.25. In this view, you should be able to land on 4.25. Right there. And so let's plot this point according to the numbers that Graphing Calculator is giving us. So plot the point 4.25, 20.4797. So start a new point, do Control, and plot this point, 4.25, 20.4797. So if I do that, choose any color you want. I'll do black. And there it is. And I'll take the crosshairs off. So everyone able to do that? We good? All right. Is that point a point on our graph? Is that point a point on our graph? Yes or no? Maybe not, you're saying? Why not? Okay, she said, so the 20.4797, Is that an exact value or is it an approximation? Probably a decimal approximation. There's probably, like she's saying, there's probably more decimal places. So is that point that we graphed, is it on our graph? No, it's not. Okay? So now what I want you to do is plot a point at t equals 4.25 that's on the graph. Plot the point at t equals 4.25 that is truly on the graph. Go. You can do it. You know how to do it if you're paying attention. And that starts this series of questions that I have for you. So that's part A. Plot the associated point for 4.25 days on GC, this time without using a decimal approximation for this height, for the height. And that point is going to be called P. And then once you got that, I want you to work through A through F. Okay, so this is to get you thinking and kind of putting together some ideas that we've talked about and giving you some challenge. So we'll walk around and help you. Work on this for about 7 or 8 minutes, see if you can make progress. But for part A, we want to make sure that that point is truly on the graph, not an approximated output. So if you want to, we'll walk around. If you want to show us your progress on these, and we'll check for you to see if you're on the right track. Okay? If you don't have graphing calculator, write down the command lines. Okay? Go ahead and write down what command lines you would use to create these, and we can check those as well. Okay? Excellent questions to see if you're getting what's going on. Remember, function notation, you need control 9. Control 9, not shift 9. You got to use control 9 using finding function notation. You're working through A through F. Want me to check your function notation? You know what you do? You're writing everything down. Mine's actually off. What does that minimum do? Is that a graph? Is that all? So then, and then that's now E is going to be your graph based starting with the y-axis. It says starting from the y-axis and ending at E. And then with on the x-axis to your yeah, you know, it's like a new function. How is K defined? What is K about? Another plan. I'm talking about the other plans. It maintains this height at all times. So it's not going to be
So the next one, you're graphing a vertical line segment in the x-axis.
Okay, now you're going to graph that starting from the y-axis and ending at point P. That's cool. So how does we get this graph to start and stop at 0 and x-axis? No, it's not scaling. So this is starting here and ending there. How did we do that? What's that? Well, not t because it's graphing it. Right? Okay, let's talk through these real quick. We still got more to do, so we want to make sure we have time. How do you get the actual point? Well, in the y-coordinate, put the exact value of the output, which is represented by h of 4.25. See, so there's great use to this function notation because it gives us the exact output instead of a decimal approximation here at whatever input you want. So now it looks like it's in the exact same place, but now we know it really is a point on our graph. Okay? What does that point P have to do with input and output? That should be easy. What does it have to do with the input and output of H? Well, so it's a particular input together with the associated output. The input is the x-coordinate. The associated output is the y-coordinate of that point. That's what you should have said. Okay? Where is this value of input shown for point P? Here. Where's the value of output, h of 4.25, shown in this graph? Here, on the y-axis. That's where you look for that value. The point P represents those values taken together, but the values themselves we reference on the axes. Okay? Okay, so now we have a new function called k, and it's the height of a different plant that never changes in height and has the height of our sunflower at 4.25 days. So we're going to find a function, capital K, control 9, remember? Use anything we want. I'll use A. So you can use any placeholder you want. What will the rule be for K? H of, it always, doesn't matter what the input A is, it always has this height, H of 4.25. And now, I want to graph that. So I'm going to graph y equals k, control 9, of x from what to what? So from 0 less or equal to x less than or equal to 4.25. Choose bold colors, these, so you can see what's going on. Got it. So we define the function k that has that constant value, and then we're going to graph that from 0 to 4.25. Now we want to graph the vertical line from the x-axis up to point P. How do we graph a vertical line? That's going to be x equals what? 4.25 from 0 is less than or equal to. Now we have a range of y values. So x is constant at 4.25. So we're getting every x value of 4.25 over a range of y's starting at 0 up to h of 4.25. I hear lots of you getting this right. These are the kinds of things you need to know how to do and understand. And again, use a nice bold color. Use purple again. There it is. Okay, so variable constants. So it's got just a little time left, really important. Here we go. So n, lowercase n, if you come here, if you hit lowercase n, slider pops up at the bottom. So n is a parameter just like any other parameter that you can pick, except for that now you can physically control the value of n on the slider rather than having to say n equals 7, n equals, by changing it up there. So now you can physically change the value of n, and then anywhere that n shows up in your command lines, it will take on the current value in those command lines. So for instance, here's this red point that we graphed. So if I do 6, or say n30, no, that's not the red graph. Let's see, what is that? There we go. So instead of 630, if I do n30, what's going to, when I hit graph, what's going to show up?
X value from 30 on the axis.
No, it's going to plot the point n30. This is plotting a point. So it's going to plot the point 430 because the current value of n is 4. What happens if I change n? What's going to happen? What's going to happen when I change n? How will it, on the x-axis? So if I change n, say to 7, then it'll show as 730. So what will happen to this point as I change the value of n? It's going to slide left and right. See that? So now here n equals 0, n equals 2, n equals 8, n equals 10. So whatever the current value of n is, it's going to plot the point n comma 30. So it gives a change. We can manipulate the x coordinate, and the y coordinate 30 is fixed. Okay, so see if you can, in the time remaining, see if you can do this. It's a little fast. So when you click on the n, you can change the parameters on it.
So the larger the number, the slower it goes.
The number of steps, yeah. If you increase the number of steps, so it's doing more steps in between.
Okay.
Yeah.
Thanks.
Yeah, it's not about speed. I mean, I'm using it as speed, but it's about how many steps in between. So here we go. There's 3 elements here. There's that horizontal line that we graphed. There's that vertical line, and there's the point. But now it's according to, so n is the x-coordinate. N is the x-coordinate. Can you create this? So rather than having that static, stationary for x equals 4.25, do it for any value x equals n, and then when you change n, it'll change. Go, see if you can do it. So our point, n h of n, will take on the point on the curve for whatever the current value of n is. Horizontal line, y equals h of n. The output, constant output at the current value of n. And then x equals n from 0 to h of n. Okay, all the homework for Tuesday will be on Blackboard.